Welcome to the product presentation on the overview of Integral CSM++. This presentation is going to talk about what CSM++ is, the motivation behind developing CSM++, and how it helps us introduce a new level of multidisciplinary analysis and design capability when used in conjunction with CFD++. What is CSM++? CSM++ is Metacomp's in-house finite element-based structural mechanics and dynamics software. It was designed specifically to work seamlessly with CFD++ to carry out multiphysics simulations. Why do we need yet another finite element-based structural solver? CSM++ was developed for the following reasons: to have a tightly coupled structural and flow solvers in modeling fluid structure interactions, to enable a tightly coupled FSI setup process with an easy and consistent user experience, and above all, to have control and flexibility in tailoring the fluid and structural solvers and their coupling algorithms according to customer needs. CSM++ analysis procedure can broadly be described in three parts: geometry creation, model setup, and post-processing of results. In geometry creation, CSM++ allows you to either create a geometry or import an existing geometry and generate a mesh. The model setup consists of defining a problem, defining material properties, and specifying loads and restraints, along with other optional things like family creation, coordinate system specification, and element properties for 1D and 2D problems. Finally, CSM++ helps you post-process your results with a solution visualizer built in, showing displacements, stresses and strains, and mode shapes for eigenvalue problems. Additionally, it lets you view time histories, plot variables over certain families, and auto-save these results. I'll first introduce some of the features of ICSM++, AUI, the Advanced User Interface. The AUI is part of Metacomp's Integral Computational Multiphysics framework. It shares common features and functionalities for mesh generation, CFD, structural analysis, and the visualization of results. It has design elements and UIs that is consistent between all ICMP-based products to have a simple and intuitive guided problem setup process. The AUI enables a powerful and user-friendly experience at the same time. The AUI consists of several components such as the menu bar, a toolbar, a canvas to display your geometry, a notebook, several pages within the notebook. For example, in CSM++, there are 3 pages: a geometry page, a model page, and a meta-FSI page for FSI analysis. Each page can have several trees. Here you see an action tree and a boundary tree within the model page. The action tree consists of several action items and a corresponding action panel. Each action item has a status indicator next to it, depending on whether the corresponding action panel has been completed or not. Completed items show up with a green check, and an incomplete panel will show up as a red X. The panels within the AUI are dockable and resizable to better suit the user's preferences. The AUI enables an intuitive problem setup process where the user is guided in a logical manner from the first action item to the last. Additionally, a thinking engine adapts these action tree items based on selections from a previous and current action panels. Let us now go over some of the basics in CSM++, starting with geometry creation. In CSM++, the user can create 2D and 3D models. They can sketch simple geometries involving points, lines, triangles, and quadrilaterals, work in several different coordinate systems, create multiple parts, and merge into one. The user can then take advantage of the built-in mesh generation capabilities within CSM++. The element types available are 1D elements for beams and trusses, 2D triangular or quadrilateral elements for shells, membranes, and solids, 3D tetrahedron, hexahedron, pyramid, and wedge elements for 3D solids. Each of these elements support different element topologies such as linear or parabolic as applicable. CSM++ can also import most meshes created in other commercial tools such as Abacus, ANSYS, Nastran, and others. Additionally, CFD++ grids can be converted to CSM++ format. In addition to just importing meshes, CSM++ can do a full model import for certain problem classes such as Nastran input files. Let us now go over the basics of the model setup within CSM++. Here, the user chooses the analysis type, the solution type, the modeling type, and the solver type. For the analysis type, the user can choose between a structural or a thermal analysis. These options appear in the AUI as follows. For the solution type, the user can choose between a static, a dynamic, or an eigenvalue analysis. These options appear in the AUI as follows. For a given analysis type, the user can select a modeling type, whether it is a nonlinear or a linear analysis. Within a nonlinear analysis, CSM++ allows for geometric and material nonlinearities. These options show up in the AUI as follows. And finally, the user can choose between a direct and iterative solver. These options appear in the AUI in the numerics panel. Let us now go over some of the details of the model setup process in CSM++. First, family creation. CSM++ allows you to create families of nodes, edges, or faces. These can be useful when applying loads, restraints, or simply post-processing results on entities smaller than entire boundaries. To create a family, the user simply selects the relevant entities, drags and drops them into the Families action panel. Next, let's look at creating user-defined coordinate systems. Creating a custom coordinate system to work in can have several uses, such as to define material orientations for anisotropic materials, to assign local coordinate systems for element properties, such as beams, springs, or to restrain specific degrees of freedom within a coordinate system. To define a coordinate system, the user can specify a set of base vectors or select nodes or node families to serve as points on each of the axes. Next, let's look at defining material properties. CSM++ allows you to define linear or nonlinear materials. Within linear, the user can pick between isotropic, orthotropic, or anisotropic materials. Additionally, the user can define a material coordinate system if applicable. CSM++ provides three nonlinear material models for large strain applications: the Mooney-Rivlin model, the Ogden model, and the Neo-Hookean model. CSM++ also provides nonlinear material models for elastoplastic materials. These models are based on the J2 flow theory of plasticity and offer three choices of hardening laws: power laws, exponential, and piecewise linear. For problems involving beam elements, CSM++ provides an easy way of defining beam sectional properties. The user can select between one of 20 different sectional geometry templates or directly specify the 6x6 stiffness matrix. Applying restraints. CSM++ allows the specification of a fixed or an applied restraint, where a displacement or velocity is specified. These restraints can be applied on families created by the user or entire edges or faces of the structure. Applying loads. In CSM++, the user can define several load sets, each consisting of concentrated or distributed loads. Concentrated loads could be forces or moments, and distributed loads could be pressure and surface traction. For transient problems, the user can also specify an arbitrary load factor. These loads can be applied on families created by the user or entire edges or faces of the structure. Initial condition specification. For transient problems, the user may wish to specify a set of initial conditions for their problem. This can be done in two ways in CSM++. The first method is a file-based initial condition specification. This is useful when the user wishes to conduct a transient analysis about a predetermined static equilibrium state, where the user can specify the solution of the static analysis as an initial condition for the transient run. CSM++ also allows the specification of initial condition sets, where displacements and velocities can be specified on all or select node families. FSI options. When running FSI analyses, CSM++ lets the user select the wetted boundaries that are involved in load and displacement transfer in FSI process. Let us now go over some of the additional features that are in CSM++. Thermal stresses. CSM++ can compute thermal stresses in a static or transient structural analysis. Additionally, material properties can be assigned thermal expansion coefficients along with mechanical properties. temperature-dependent material data specification is supported, including the specification of thermal expansion coefficients. Creation of special line elements. In addition to all the element types presented before, CSM++ also supports the specification of rigid, spring, and beam elements connecting nodes or node families. Rayleigh damping. For linear transient analyses, the user can specify a mass proportional damping and a stiffness proportional damping. For nonlinear transient analysis, the user can only specify a mass proportional damping. No stiffness proportional damping can be specified due to a constantly updating stiffness matrix. Additionally, for nonlinear analysis, the user has a choice of update methods to the tangent stiffness matrix, where the stiffness matrix is updated every step, every substep, or is updated based on the deformation. Multi-point constraints. CSM++ offers 4 methods of enforcing multi-point constraints: the penalty method, which is the default, a direct substitution method, Lagrange multiplier method, or an augmented Lagrange multiplier method. Large overall motion. For some problem classes, it is important to model a large overall motion of the structure, such as in rotor blades and flapping wings. CSM++ allows a file-based motion specification where the user can provide an arbitrary motion of the structure for the duration of the analysis. Follower forces. CSM++ allows the specification of follower forces in nonlinear static and nonlinear transient analyses. To designate a load set as a follower force, the user first checks the large displacements expected box in the physics action panel, and then the load follows deformation box in the nonlinear options panel. An additional FSI option within CSM++ is the specification of a load factor. This load factor determines how the forces and moments are being transferred from CFD++. Let us now look at a few example validation cases, starting with the nonlinear statics of a beam under a tip force. Here, we have an isotropic cantilever beam subject to a series of tip loads. For the given load levels, it's appropriate to conduct a nonlinear static analysis with large deflections and slopes expected. As can be seen from the visualization below and the results provided, CSM++ is able to closely match corresponding experimental results and an ANSYS nonlinear model. The next example also involves the nonlinear statics of a cantilever beam, but this time subjected to a tip moment. For this case, an analytical solution exists that can be used for validation purposes. The animation below shows how a prismatic beam can be bent into a full circle with the application of a tip moment. The results obtained by CSM++ can be seen to compare very favorably with the exact solution using only 20 beam elements, while RCAS results with the same mesh density show larger errors. The next case involves the nonlinear dynamics of a flapping wing. Here, a rectangular wing modeled as a shell undergoes prescribed flapping and feathering motions. This is a nonlinear transient analysis with a large overall motion specified. To compare with existing numerical results, the time histories of the tip displacements of the shell model are shown here. The solution can be visualized in the AUI as shown in the animation below. The next two cases highlight CSM++'s ability to carry out eigenvalue analyses and compute mode shapes. The first model is of the hyaronized wing, of which a Nastran structural model exists. Here, we have used the ability of CSM++ to import full models, not just the mesh, to conduct an eigenvalue analysis. This is a 3D solid model involving parabolic tetrahedrons, point masses, and Nastran RBE2 rigid elements. The eigenvalues of the hyaronized wing that we determined are provided below, along with comparisons to experimental results and Nastran results. Visualizations of some of the mode shapes are also shown here. The second model used for conducting an eigenvalue analysis is the AGOD wing. This has been modeled as an orthotropic cantilevered shell with variable thickness. The root section is only partially clamped, which can be done with the ability to create node families. The frequencies and mode shapes of the AGOD wing that we determined are provided below, with comparisons to existing experimental results. To summarize, CSM++ is Metacom's in-house finite element-based structural mechanics and dynamics software that is designed to enable tightly coupled multiphysics simulations by working seamlessly with CFD++. CSM++ was developed to have tightly coupled structural and flow solvers in modeling fluid structure interactions and to have control and flexibility in tailoring them and their coupling algorithms according to customer needs. We have seen that CSM++ is part of Metacom's Integral Computational Multiphysics Framework, or ICMP, that enables a unified, intuitive, and simple problem setup process that is simultaneously powerful and user-friendly. We have presented many of the basics of the intuitive problem setup process, starting with geometry creation and meshing or importing existing meshes and full models. Next, we presented all the options available to the user regarding model setup such as analysis type, solution type, modeling type, and solver types, along with the detailed list of modeling capabilities. We have also looked at some of the advanced features supported by CSM++, such as choice of update methods for nonlinear analyses, choice of enforcing multi-point constraints, and specification of large overall motion and follower forces. And finally, we have provided a collection of 2D and 3D structural mechanics validation cases to provide a glimpse of the kind of analysis and the quality of results users can expect from CSM++. Thank you for your attention. For more information on ICSM++ or other Metacom software products, please contact info@metacomtech.com.